In this video, I'm going to be running some path integrals over vector fields. Working multivariable calculus homework 4.4. So we're going to start by just running some nice path integrals. The integral of x dx, where c is defined by y equals x to the 3. So step 1, parameterize your curve. C is going to be given by r of t equals y equals x to the 3. I'll just let x be t and y be t to the 3. If x is going 0 to 3, then t should be going 0 to 3 as well. Okay. Let's see, x is t, dx is dt. Okay, so this is going to become the integral from t equals 0 to t equals 3 of x is t. dx is dt. There's some sort of meaning that you're supposed to be taking out of this, and I'm just not seeing it right now. Why it doesn't really matter x dx. Oh, this must be some sort of vector field that there's something like kind of trivial about this vector field that we're dotting with dr. Okay, because it's going to be x in the x component and 0 in the y component. I don't know, probably doesn't think about it too much. This is going to be 1/2 t squared as t runs from 0 to 3, and that's going to be 9/2. I don't know, maybe you see what you're supposed to see. Let me know in class next time. 1b is going to be y dx minus x dy. C is y equals x squared. So step 1, parameterize the curve. Y equals x squared. X runs from 0 to 2, so t can also run from 0 to 2. All right, I'm going to need y dx minus x dy. Well, so I've got all my ingredients, and I'm just going to put them together into this integral. This is going to be the integral as t runs from 0 to 2 of y dx is t squared dt minus x dy is going to be 2t squared dt. So this is the integral from 0 to 2 of, let's see, negative t squared dt, which is negative 1/3 of t to the 3rd, as t runs from 0 to 2. And so I think that will be negative 8/3. And I think that's probably negative, because if you plotted the slope field f of x and y equals y in the x component and negative x in the y component, I think it would probably have, just like a pattern that's the opposite of y equals x squared. So y equals x squared, if you're moving up from x equals 0 to x equals 2, would be going against the grain of the vector field, and therefore the work done would be negative. All right, part C. This is 3-dimensional, but it's going to be the same process. I'm going to say, all right, so they already defined r of t for me, so I don't need to do that. I need z equals t, so dz equals dt. I'm going to have x squared is going to be cosine squared t. dy is going to be y prime of t dt, secant squared t dt. That's really convenient. And then y is equal to tangent t. That sounds troublesome. And dz, dz is dt, so I need actually dx over here. Lost track of what I was doing there. Dx is going to be negative sine t dt. So in total, I'm going to have the integral as t runs from 0 to pi over 4 of z dx, that's negative t sine t t dt plus x squared dy. Well, x squared dy is going to be cosine squared t times secant squared t is 1 dt plus y dz is tangent t dt. Okay, this one would require integration by parts. This one would be a u with, writing tangent t as sine over cosine and letting u equal cosine of t. We don't want to go there. That's too much. Let's just use a calculator. All right, we're going to integrate from 0 to pi divided by 4, negative t sine t plus 1 plus tangent t. Okay, no domain issues, tangent, yeah, okay, we're good. And we get 0.980. Right, and then 1d, looks like it's more of the same. So they've got r of t defined for me. T is going to run from 0 to 1. So I just need to write down y and dx and z and dy and x and dz. Okay, so y equals t cubed. dx is going to be, okay, the derivative of this is negative t to the negative 2 dt. Okay, z equals t squared. dy is going to be 3t squared dt. And x is 2 plus t to the negative 1, and dz is equal to 2t dt. Okay, I see where this is going. Okay, so I might put these together real quick. Y dx is going to be negative t dt. Right, because t to the 3 times t to the negative 2 is going to be net 1 power of t. All right, t squared times 3t squared is going to be 3t to the 4. And x dz is going to be, okay, if I multiply in that 2t, I'll have 4t plus 2t times t to the negative 1 is just going to be 2. Yep, there we go. There we have it. So we're just going to add all these together, probably factor out the dt out the back, integrate from 0 to 1, be happy. Okay, so negative t plus 3t to the 4 plus 4t plus 2 dt. Okay, but I see terms that I can combine. So I'm going to do that. That's the integral from 0 to 1 of 3t to the 4 plus 3t plus 2 dt. Take an antiderivative. Let t run from 0 to 1, and I'll end up with 3/5 plus 3/2 plus 2 minus 0. And, well, I think that'll be a safe place for me to stop. It's a number that's equivalent to the integral. All right, compute f dotted with dr for this f and this c. Okay, we can do this. Okay, so integral of f dotted with dr. Well, c is a line segment from 0, 0 to 1, 3. All right, so I got to parameterize that. Okay, so y equals 1/3 of x. You could definitely do t and 1/3 t. Do the same thing. I think I'm going to let y is going to run from 0 to 3, and y is t, so I'm going to let t go 0 to 3. If you'd done t and 1/3 t, you would let t run from 0 to 1. No, you would still let it go from 0 to 3. Yeah. Wait a second. 0, 0 to 1, 3. 0, 0. Nope, y is equal to 3x. Okay, I was like, what wasn't working. Yeah, y equals 3x, so it's going to be t and then 3t, and that will be t running from 0 to 1. Yeah, that didn't seem right at all. All right, and then, okay, so I'm trying to think, how did I do this yesterday? I like how was I writing it? So f in terms of t is going to be 1 plus x squared is t squared. And then x times y squared is t times 3t times 3t, that'll be 3 total powers of t, and 2 3's, that's 9. dr is going to be x prime of t and y prime of t dt, so that's okay. And so the integral over curve C of f dotted with dr is going to be, the integral as t runs from 0 to 1 of 1 plus t squared dt plus 9t to the 3 times 3 dt, so it's going to be 27t to the 3 plus t squared plus 1 dt. All right, I'm going to anti-differentiate. And then I'm going to get 27 over 4 plus 1/3 plus 1 minus 0 plus 0 plus 0. And, well, there we'll have it. Okay, y equals x to the 3 from 0, 0 to 2, 8. Okay, so C is going to be parametrized by r of t equals t and t to the 3 as t runs from 0 to 2. Okay, then I'm going to just like before, get f in terms of t and dr in terms of t. So f equals x and 2y. dr is going to be the derivative of x and the derivative of y dt, so 1 dt and 3t squared dt. So the integral over c of f dotted with dr is going to be, the integral as t runs from 0 to 2. F dotted with dr is going to be t plus 6t to the 5 dt. That's nice. And this will be 1/2 t squared plus 1t to the 6th. This t runs from 0 to 2. So half of 2 plus 2 to the 6, 64. Okay, and that's going to be 66. So I'm going to probably need a whole sheet for this one. Alright, so f in terms of t is going to be x, y, negative 5z. dr is going to be dx dt, so negative 2 sine t dt, 2 cosine t dt, and 1 dt. So I'm going to end up, this is going to cancel off real nicely. I'm going to have negative 4 sine t cosine t plus 4 sine t cosine t ends up being 0, negative 5t dt. Okay, so this is the same as the integral from 0 to 2 pi of and that's going to be negative 5 halves of 2 pi squared minus 0 squared. So that'll just be that. Okay, this is 2c. Did not take nearly as much room as I thought it would. About 3 dimensions. More room. Alright. F is e to the z, e to the x minus y, and e to the y. C is, okay, you can't see what the blue path was, but this was the blue path. Okay, and you can do whatever you want. You can parameterize this as one piecewise smooth curve, you know, with 3 different pieces, or you could just do it 3 different times and split the integral up into 3 integrals and add them all together. Doesn't matter. Okay, so I think maybe I'll split it up into 3 integrals. It's something different. I usually just parameterize it as one piecewise smooth curve, so I'll switch it up. Okay, so I'm going to call this curve C1. This is going to be C2 and C3. C1, x and y are both 0. And z is running from 0 to 1, so that's going to be 0, 0, t. And, well, okay, we've got that. We've got f. In terms of t, well, that'll be e to the y, which is, oh. Hold on. Okay. F of r of t is going to be e to the t. E to the x minus y is e to the 0 is 1. And e to the y is also 1. So f dotted with dr is just the integral of dt. Oh yeah, and this was t running from 0 to 1. Okay, so the integral from 0 to 1 of dt is going to be 1. Okay, so on curve 1, I've got 1 unit of, I guess, work done by the vector field. On C2, okay, r is going to be equal to, okay, z is 1 the whole time. X is going to be 0 the whole time, and y is running from 0 to 1, so we'll let y be t. T running from 0 to 1, you can't even see that. And so, yeah. Okay. And I need to translate f into t's. Okay, so f of r of t is going to be e to the z. That's e to the 1, e to the x minus y, e to the negative t, and e to the y is e to the t. Okay, so f dotted with dr is just going to be e to the negative t dt. So then this will be the integral from 0 to 1, e to the negative t dt equals negative e to the negative t So this is going to be 1 minus 1 over e, right? Because then when I distribute in the negative, this 1 becomes positive, and then this, okay. Okay, that's the second part. Then I'm going to add to the first part and then add to the third part to get my total path integral. Then on C3, okay, x is running from 0 to negative 1, y is stuck at 1, and z is also stuck at 1. Okay. So I'm thinking I've got negative t 1, 1. Let me make sure that's right. Yep. As t runs from 0 to 1. Okay. Dr equals negative dt, 0 and 0. F of r of t is going to be Right, going back to f is e to the z, and z is 1. And that's all I'm really going to need, but e to the x minus y is e to the negative t minus 1. And then the third component is e to the y is just going to be another e. So the integral of f dotted with dr is going to be the negative integral from 0 to 1 of e dt, which is going to be negative e. Yeah, that's interesting. Whatever. So in total, the integral over curve c of f dotted with dr is going to be what I get from doing this on c1 plus what I would get doing it on c2 plus the one on c3, which is going to be, the first one was 1 minus 1 over e, and then a negative e. So that's, I don't know, some weird number. That was odd. And then, nice, the last one is just much more conceptual level. Okay, determine if the integral of this vector field over that path is positive or negative or 0. And that's going back to the idea where if the path, the orientation of the path is going pretty much with the vector field arrows, then you're going to have a positive dot product, you know, from the tangent vector to the vector field vector. And you're going to add all those up, and you're going to have a positive path integral. So I know that A is pretty much going with the grain, right? There's a lot of left to right motion on this, and we're also going left to right. Now I do recognize that at the beginning it's going up and the curve is going down, so there would be a little bit of negativity in there, I think. But even still, that looks like an acute angle here, there. So I'm not sure that I think it's going to be positive the whole time. So I'm thinking this one's positive. Okay. Now I remember that these were close. These weren't as obvious as the usual. I've seen other problems like this where it's a lot more obvious. But I think that this one's going to be 0 because although it's positive through here, it's like very much with the grain, it's very against the grain through there in its symmetry. And then in the middle, where I'm going to highlight in red, it's very much like sitting against the, or like orthogonal to the vector field marks. And so we know that the dot product of two orthogonal vectors is 0. And so if I was, I had an area where it was positive, an equivalent area where it was negative, and then an area where it was about 0, I think that this one's going to be the closest to 0. And then this one over here, okay, I'm not sure how I would know that it's negative, but we feel like it's going to be negative based on discussions we've had in class, because although it is pretty much with the curve here, at about here, it starts to turn around and push against the vector field, and then that would end up doing, the vector field would end up doing negative work. So we think that this one's negative, but it's not super obvious, I will admit. And the amount by which this is positive compared to this negativity, who knows? But that's the idea. With the grain is positive, against the grain is negative, always orthogonal to the vector field marks, that's going to be a 0. Okay, and we'll have more to say about when the path integral comes back 0 in the next lesson. I think that's all I'm going to have for you for this video, so thanks for watching.